Yes, thank you, Phil. It was really poetic that Christian started this meetup with a talk about VVC because I'm ending it with actually the opposite of it. I'm ending it with a more radical approach to compression and not an iterative progress of it. So over the last 2 years, there's a paradigm shift emerging in the image and video compression technology, and I want to share with you the story of learned-based compression. My name is Besenbruch. I'm here today with my co-founder Aslan Savha. Where is he? Well, he's somewhere here. There he is. We are from Deep Render, and we are a product-driven research group that is developing learning-based compression approaches. So let's jump in. Really quickly to get everyone on the same page, even though it's probably not needed at all. What is compression? We have an input file, we have an output file, video or images. We have an encoder that reduces the file size of the input file, and then a decoder pipeline that on the receiving side restores the image, and in this case we're talking about lossy compression, so we allow to have some errors in there for a reduced file size. It's the rate distortion trade-off. What is out there? What are the standards nowadays? Well, on the image side, we have JPEG, JPEG 2000, WebP, and the best one so far, BPG, Better Portable Graphics, that's H.265 Intra. And on the video compression side, we have the royalty-free codecs from Google and AOM, VP8, VP9, and AV1, and the codecs from the MPEG group with ETU Corporation, H.264, H.265, and soon, hopefully, H.266. But before we jump into learning-based compression, we have to do one part before that, and that is the importance of compression. Because we see that there is a huge problem on the doorsteps of our community that is not fully appreciated yet, and we try to raise awareness of that. And to start it, the question is the importance of compression. Does compression actually influence your daily life? Or let's say the daily life of the average citizen in a significant way. And the right answer to this question is yes. And here is why. Here are some statistics on it. Well, what are the current compression ratios? For images or video files, especially 4K video files, compression ratios in lossy compression of 250 times smaller file sizes compared to the raw version are not unusual. So if we don't, I probably clicked somewhere wrong. If we don't have in a world where we would not have compression, that means that we need 20 to 250 times the bandwidth available to our homes in fiber cable to get the same quality of entertainment or productivity. And you might think that, okay, why is that so significant for the average citizen if they see some artifacts on Netflix or YouTube? That is not really important. However, another interesting statistic is that 80% of the global traffic, if we look at the modern internet, is made of image and video data. So we can argue that actually a core technology of the modern internet is compression, especially image and video compression, when maybe one of the foundational layers is bandwidth because somehow the bits need to get you to your home. One of the next most important technologies is compression technology, because otherwise we cannot pay for all the bandwidth we need. So what is the problem I was talking in the introduction? If we already have really good compression and it is moving forward with the VCC, well, there are two sides of it. On the one side, we have an exponential growth in data generation that is going on for quite some time already. We have here the global traffic in exabytes and here time axis. And when we only sent 70 exabytes over the internet in 2014, 2018 we had 150 exabytes. We're projected to be at 400 exabytes in 2022, and the projection is from 2017, and in 2018 we actually went above 150 exabytes globally per month. That means that we need to lay more and more fiber cables to our homes to keep up with the bandwidth demand, and with our consumption, and with our productivity. In the past, this trend was partly offset by better image and video compression. If 80% of the global data is image and video compression, and we get every 6 to 8 years a 50% improvement in these technologies, then we can offset this exponential growth and make it cost efficient for us to get more entertainment and more productivity out of the internet. And here's where the problem really starts. Over the last decade, the efficiency gain in traditional compression shows diminishing returns. While we were quite spoiled in the early days and got 50% smaller file sizes for the same visual quality in earlier days, this kind of stopped with H.264. For instance, from H.264 to H.265, the drop was more in the range of 31%. And from HREC to AV1, the drop was more in the range of 20%. Even worse, depending who measures. I included also a graphic from the BBC, because we use their location. They tested on their data set AV1 against H.265, and they saw that actually there was no progress made at all, especially not in 1080p data, and only a really small progress in 4K data. So what that means is that everything we have known from the past, that we get way smaller file sizes as time goes by, might be wrong if we're looking into the future. And why is this the case? Why is this happening? And is this maybe only happening right now and we can get back to growth rates in compression efficiency? Well, if we look at the traditional compression pipeline, how it looks like, in really simplified form. We have the macro block tiling, motion prediction, transform coding, quantization, and the entropy model, and maybe in-loop filtering for video. And the problem is this did not really change for very, very long time. For instance, in the transform coding part, codecs still use DCT that was used in JPEG. And JPEG is not really an efficient standard by today's bit rates anymore. And this pipeline has an additional problem. All these parts are designed independently. It's handcrafted. And for instance, the transform coding part can only use linear functions only. It will become these properties will become very important later on. There is a limit how much further we can iteratively improve the same idea that was there already for over 2 or 3 decades. So to summarize, the problem in front of our door is that there's too much data and too little bandwidth, and that our helper that helped us in the previous years or decades, compression advances will most likely no longer offset data growth. And this points at a rather bleak picture of the future. So here's a happiness slide for everyone. And let us come to a solution we are proposing and advocating. And to start that off, let's start off with some advances in artificial intelligence. You're probably accustomed to reading in the news articles like Rise of the Machines, AI beats humans in multiplayer shooter. Microsoft AI beats humans at speech recognition. Machines just beat humans on Stanford's reading test. Or AI beats humans at image recognition. And the key idea is, why is artificial intelligence so powerful in so many different domains? Well, to see why, we can go back to the slide. The properties of these algorithms, where the same properties old, for instance, image classification tasks or computer vision algorithms had. They were independent, handcrafted, and often only used linear models. And when the artificial intelligence revolution taught us one thing, is that these properties are exactly how we should not design a successful algorithm. Successful algorithms, and that obviously applies to image and video compression as well, should be designed with context correlation in mind in an end-to-end pipeline, meaning that every subroutine in the algorithm can talk with each other and can influence each other's step. It has to deploy non-linear functions, because this is unfortunately how the world works. It's more complex than just linear predictions. And it has to show adaptability to its source. There should not be one single pipeline for all images or all video. And if we go up from these properties and think about artificial intelligence, it gets quite clear how the future of compression should look like. It should be a neural network approach, and this is a radical paradigm shift, because that means that we should throw everything out developed in the 80s and mostly ignore it and rebuild compression from scratch to get back to efficiency improvements we need and want. So if we say that, let's look at some eye candies to show you some of these results, because this field is active probably since 2 to 3 years in the research community and is very close to getting deployed. So here is an image as a really low bitrate to look at some artifacts, and I hope we can all see the problems in the upcoming images. This is a BPG compressed image at 2 kilobyte. And this is our version of learned image compression that we name biological compression in comparison with a smaller file size. And I hope we can agree that the block-based approach has some nasty artifacts, whereas the non-block-based approach looks much more perceptually pleasing. Oops. And I want to show you some of the advantages these approaches promise us for the future to get you excited about it and look them up on your own, because I cannot fill all of the advances in a 10-minute talk or 20-minute talk. So let's look at the artifacts we are accustomed on from the traditional pipeline and look how they translate to a new approach. We took these 2 images here, compressed within roughly 25 kilobyte with BPG and a learning-based compression approach. And the first thing we can notice is if we look at this line very carefully, and believe me, it looks better on the laptop, that in the BPG approach, we sometimes can see ringing artifacts when there should be a straight line. And this is an inherent problem of the pipeline, because if it cannot allocate enough bits, the frequency transformation can create ringing artifacts. Whereas an end-to-end pipeline that can shift bits around wherever it wants has to have these limitations, as we can see on the straight line here. I might share the laptop images with you later. The same is when we look in the bottom right corner. This is only mud, but high detail mud with high frequency components in it. In the BPG image, it gets very, very blurred, because the image does not have enough bits and cannot decide where it wants to allocate it. It allocates it on a block-based system and not on a global system. Whereas in the learning-based approach, we can put much more details into this mud here, or into this dirt at the bottom. And then another limitation that we can overcome is wrong intra-predictions. It's actually really difficult to see here, but if they would be sharper, what you can see is that there are some wrong intra-prediction modes chosen here, or not optimal intra-prediction modes, because the movement does not continue smoothly here, and that will create artifacts, whereas this would actually be sharp, because a learning-based approach does not has these limitations built in. So these are the 2 images if someone wants to compare the quality in its entirety. So to summarize, we have to build a new AI-based foundation for compression to overcome the traditional pipeline and its limitations. Where are we? Where is the community right now? I would argue that we are at the end of phase 1. The feasibility is proven through different research groups worldwide, and we can now look forward to hopefully soon see that in pilot cases deployed in the market in phase 2. From our personal experience in image compression, we expect bandwidth savings for the same quality of 50 to 75% in the first codec we release, and many more improvements are possible. And then what is the end goal for biological compression or learning-based compression? Well, using artificial intelligence in compression uses, roughly speaking, similar mechanisms than the human eye, because neural networks are inspired by neurological processes. And Penn University was able in 2012 to roughly measure the bandwidth of the human eye. And let me just tell you, in this way, the human eye is incredibly more efficient than HVAC or H.266. In fact, depending on how you want to measure the frame rate or the resolution, or if you actually want to measure it directly or indirectly, the human eye can be up to 5,000 times more efficient than the best video codec we have to date. And we're not saying we're getting there, but even if we're just getting close, it will be an amazing future we are looking forward to. So yes, thank you all, and if you'd like to know more, please find us on LinkedIn or visit our website.